Okay, so here's the theorem that I promised. So suppose we have a commutative ring and an ideal frac M in R, then frac M is maximal if and only if R mod it is a field proof. All right, so let's see. Let's do the forward direction first. So let's suppose M is maximal. And let's take some x in R minus M. Then by the lemma that we proved in the previous video, there exists R prime in R and Y prime in M such that 1 is XR prime plus Y prime. Or equivalently, 1 plus the ideal generated by M, so the coset that corresponds to 1 is XR prime plus Y prime plus M. But Y prime is in the ideal, so that sort of becomes 0. You can absorb it in. And so what this is saying is, if we were to take a non-zero element in the quotient, so some guy x that's not in M, so x plus M is not M, then there's a multiplicative inverse R prime. Sorry, my M's are getting worse and worse. So this is saying is if x plus M is not equal to 0 plus M, equivalently x is not in M, then x plus M has multiplicative inverse R prime plus M. Thus R mod M is a field. Okay, so that's our forward direction. So what we were doing in the previous lemma is we're coming up with a multiplicative inverse. For the backwards direction, we're going to suppose that R mod frac M is a field. And we want to show that M is maximal. Well, let's take some ideal I, such that M sits between I and R, but I is not equal to M. So I has more elements. I has more elements than M. Or yeah. All right. Since I has more elements in M, there is something in I that's not in M. So there exists some Y in I minus M. So something in I that's not in M. Okay, this means that Y plus M is not 0. So it's a non-zero element in the quotient. Okay, since the quotient is a field, there exists some Y plus M in it, such that, I already have a Y, shoot. There exists some X plus M in it, there we go, such that Y plus M times X plus M is 1 plus M. Right? Because I'm a field, I am a field, so I have multiplicative inverses to all my elements, so I have a multiplicative inverse. But the left-hand side is Yx plus M. So Yx and 1 belong to the same coset. So there exists some little m. Dang, I don't want to use M. There exists some t in M such that yx plus t is 1. That's just saying that yx and 1 are in the same coset, so they differ by an element of the ideal. Okay, so we're almost done. Then yx plus t, well, on the one hand, that's 1. On the other hand, t is in M, which is in I, and y is in I, so yx is also in I. So we have a sum of elements in I, so this sum is also in I. So I has a unit. But if you have a unit, you must be everything. Okay, so we took a random ideal that sits in between M and R, properly containing M, and we showed it actually had to be the whole ring. Thus, M is maximal. Sorry, I've used thus a lot in this proof. Oops. But M is maximal, and that's the end of the proof. So maximal ideals quotient to, when you quotient by them, you get fields. And if you've quotiented by something and you got a maximal ideal, you must have, or so you got a field, you must have quotiented by a maximal ideal.